Hello citizen of Labster and world. I'm here with my friend Jack Napier, the CEO of Everchem, to officially announce the construction of solar power plant and the energy storage system. Now, I would like to invite him to elaborate some points that are included in the construction of this project.
Morning everybody, and good morning also to Mr. President of Labster and the rest of the board members. Today I have a good news for all of you. I, Jack Napier, the CEO of Everchem Energy Storage System (ESS), will be collaborating with Labster to make new solar power plant with Everchem Energy Storage System (ESS) in the desert. So this is done purposely to provide an electrical energy for residential and industrial usage.
Jack Napier,
Ask questions?
how does the solar power plant and the ESS work?
Well, it works by...
What are your researchers saying about this?
Well, I don't think I have sufficient amount of discussion.
What organic compound are you going to use?
Wait a minute.
Is the organic compound easy to transport?
Is the organic compound used going to be bad for the environment?
How efficient is it going to be?
Is the organic compound going to be expensive?
What are the thermodynamics?
Is the compound used going to be hard to find?
Hey, come on, answer some questions.
Where are you going?
Hello. You guys saw the live news just now, right? You guys made a fool out of me in front of everybody. So you guys better come up with some answers now.
Deepest apology, sir. Now, our team will start to propose 3 compounds that is suitable to store the energy. But first, let me start with the introduction. Hi, I'm Arisha. I'm one of the researchers in the team. Labster solar power plant harnesses the solar energy in a desert region, but needs an efficient energy storage system to store the energy. Everchem ESS plant store the energy as chemical energy. So, octane has been suggested as potential compound, but 3 more compounds needs to be evaluated. This evaluation includes the thermodynamic analysis, which include the analysis of enthalpy, delta H, entropy, delta S, and Gibbs free energy. Before we start with the evaluation of the compound, we first need to understand the flow of the energy. First, the energy will be collected from the solar power plant as solar energy. This solar energy will be converted into electricity. Then, the electrical energy will be stored in chemical compound as chemical energy. It works like a battery. So, to release back the energy, this chemical compound will be combusted to release the heat. This heat will be the thermal energy. So, thermal energy will be converted back into electricity. Thus, the energy could be utilized depending on the specific system design.
For this research, we have decided that the problem statement is what is the best compound to store energy instead of octane, and the objective is to determine 3 suitable compounds to store the chemical energy.
Right?
So now I would like to talk about the criteria. The first one that we're looking at here is called heat of combustion. The organic compound must produce a large amount of energy per unit mass, which in result will produce a high calorific value. The second one is the ease to store and combust it. The organic compound has to be in the most suitable form in order to store energy. We are considering also the packaging efficiency, where it can be transported in standardized containers using standardized equipment. The third criteria is the economical and pollution free. The organic compound that we're choosing will produce a lower greenhouse gas emissions. And then the last criteria that we're looking at is heat capacity, where the higher the specific heat capacity, the more efficient a material will store heat.
So the solution suggested to determine the best chemical compound is by using the bomb calorimeter experiment. The hypothesis of this experiment is the higher heat of combustion, the higher the efficiency of chemical compound to store and release energy. The Q surrounding equals to QH2O plus with the Q calorimeter, and QH2O can be obtained by multiplying mass of water with the specific heat capacity and the delta T. Q calorimeter equals to specific heat capacity of calorimeter times with the delta T, and Q system equals to negative Q surrounding. Then the delta H can be obtained by dividing the Q system with mole of compounds.
I understand.
The first compound is hexane. Hexane is a hydrocarbon in the alkene series with the chemical formula of C6H14. So the heat combustion of hexane is negative 2852.25 kJ per mole. And the phase at room temperature for hexane is liquid, which makes it very efficient to store energy and transport it in various forms of transportation. But in the environmental aspect, when combusted, hexane releases carbon dioxide.
So the calculation of the heat of combustion of hexane is QH2O equals to 28.0989 kilojoule, and then Q calorimeter equals to 4.687 kilojoule, and Q surrounding is equals to 32.77 kilojoule. The Q system equals to negative Q surrounding, and then the delta H is equals to negative 2825 kilojoule per mole. So specific heat capacity of compound is equals to 58.51.79 joule per gram degree Celsius.
Then we have the suggested organic compound, octane, a hydrocarbon compound with chemical formula C8H18 that is often used as fuel. It has a heat of combustion of negative 5,192.05 kilojoules per mole. It is also extracted from underground reservoirs, and its major component is gasoline. Since it is a hydrocarbon, it also contributes to greenhouse gas emissions.
Moving on to the next compound, decene. Decene is also an alkene series, but consists of 10 carbon atoms that bonded to hydrogen atoms. And the heat combustion for decene is negative 8,528 kilojoule per mole. And the heat capacity for decene is 5,852 joule per gram per degree Celsius. At room temperature, decene is in liquid form, but as a hydrocarbon, decene also releases carbon dioxide when combusted. Moving on to the calculation of heat combustion for decene. After the calculation, we will get the heat released by the water is 51.163 kilojoule, and the heat released in the calorimeter is 8.537 kilojoule. The heat released to the surrounding is 59.7 kilojoule. So the heat released to surrounding is equal to negative heat released by the system, which is negative 59.7 kilojoule. The heat of combustion, which is negative 8,528.57 kilojoule per mole. And for the specific heat capacity of decene, we will get 5,852.94 joule per gram Celsius. Last compound is biodiesel. Biodiesel is a renewable fuel. It is made from biological ingredient rather than fossil fuel, which make it one of the best biofuel alternative. The heat combustion for biodiesel is negative 5,986 kilojoule per mole. And when combusted, biodiesel also releases carbon dioxide. However, the carbon dioxide emitted from the combustion is considered carbon neutral.
So now I would like to show you the calculations of biodiesel, and after we've applied the formula and all the numbers that we have, we would get the specific heat capacity of the compound is 5,853.11 joule per gram degrees Celsius.
For the thermodynamic analysis, we need to view from the delta H, delta S, and delta G. Moving on to the Gibbs free energy. So we're going to use the delta G equal to delta H plus with negative temperature times with the entropy. So by using this formula, we can determine the spontaneous of the reaction that occur with the assumption temperature is 290 Kelvin.
In this study, our objective was to identify a suitable organic chemical compound amongst 3 other compounds to replace octane as an energy storage medium. So why was decene shown as the most favorable compound of them all? For starters, decene has the highest heat of combustion, which is crucial for energy release. The most efficient way as of right now is implementing carbon capture and utilization technologies. In fact, this technology works by capturing the carbon dioxide gases emitted during combustion and store it underground or utilizing it for other purposes. This can mitigate greenhouse gases. In conclusion, after serious evaluation upon each criterion, decene emerged as the most promising organic compound to replace octane for energy storage and transport. In fact, the properties of decene align with the requirements of efficient energy release, environmental sustainability, and practical implementation. Hence, decene represents a promising alternative that can contribute to the development of a cleaner and more sustainable storage compound. Thank you.
Okay, now at least I have something to give to the press.